Alright, so on examples from worksheet 5.2 part 3, I'm going to do numbers 4, 8, 12, 16, etc. with you so that you can understand this even better than you already do. So, part of this is, if I have the 6th root of 81, I want to be able to write this in a simpler form. And the way I can do that is by using rational exponents. I can think of this as the 6th root of, and then what can 81 be written with a different base, the lowest base you can think of? 3 to what power? 3 to the what? 4th, right? 3 to the 4th. So I know that I can rewrite this now as 3 to the 4th power and the 6th root. Well, what does 4/6 reduce to? 2/3. And so now I'm going to go back and I'm going to rewrite this in radical form. So here's my root, 3, and then I have 3 to the 2nd. So this is the cube root of 9. So the cube root of 9 is the same thing as the 6th root of 81. And it's a lot simpler to say the cube root of 9 rather than the 6th root of 81. I want you guys to go back now and try number 1. How would we rewrite number 1 in a simplest radical form? Try it. Carson, did you get it? Not yet? Look what I did. I have the 4th root. I've got 9 can be written as 3 squared. So now I have 3 to the 2nd power, 4th root. 2/4 can be written as 1/2. What's 3 to the 1/2 written as a radical? Radical 3. So the 4th root of 9 is the same thing as the square root of 3. They mean exactly the same thing. Let's take a look at number 8. Number 8. We have a binomial squared. What you cannot do is, you can't just square this and square that. It would not work. This is a binomial. So I'm going to have to do 3x squared plus x to the negative 2 times 3x squared plus x to the negative 2. Because they're binomials, I'm going to have to FOIL it out. So I'm going to have to do first times first. That gives me 9x to the 4th. I'm going to have to do last times last. That's going to give me 3, and then x squared times x to the negative 2. My base stays the same, and I add the exponents. What is x to the 0? No, it's not 0, it's 1. So this would be 1 times 3, so it's just going to be 3 right there. But I'm just going to keep that in mind. I go to my inners. What am I going to get there? 3, and then x to the 0 is just what? So it's 1 times 3 though, so the whole term would be 3. It's 3, and then just the x is to the 0 power. So that's 1 times 3, it's the same thing. Last times last, my base stays the same, I add the exponents. So what I have now is 9x to the 4th plus, this is 3 and this is 3, so plus 6 plus, I can't have negative exponents, so I'm going to have to write that as 1 over x to the 4th. Now, a lot of times when we're working problems like this is not a solution you see if you're taking, say, the ACTs, or even if you're doing math facts. You don't see this as one of the options, because they would get a common denominator. This has a denominator of x to the fourth. So we're going to get a denominator of x to the fourth here and here. Just getting a common denominator. So now I would have a common denominator. I've got 9x to the 8th plus 6x to the 4th plus 1 all over x to the 4th. And that's the best answer because we have the common denominator. Let's take a look at the next one. What do we do with this when we have like bases and we're dividing? What do we do with the exponents? Subtract. So we keep the base and we subtract the exponents. 1/5 minus 2/5 is negative 1/5. That's what we get for the inside. Then we have to the third power. What do we do if we have a power to a power? Multiply. So we're going to have 5 to the negative 3/5. So that means I'm going to have 1 over 5 to the 3/5. Well, that means I have 1 over the 5th root of 5 cubed. I'm not allowed to have radicals in the denominator. I need to rationalize this. So how many 5s do I need to have for my exponent in order to be able to take the 5th root? 2 more, right? So I'm going to have to multiply by the 5th root of 5 squared. And so now in the numerator I have the 5th root of 5 squared. In the denominator I have the 5th root of 5 to the 5th. Well, what is the 5th root of 5 to the 5th? And then here I've got the 5th root of 25. We're writing these in simplest radical form. No radicals in the denominator and no rational exponents and no negatives. Alright, let's look at number 16. I've got 8a to the negative 3, b to the 3/4. Now look at this. This is the root, this is the power. So what is everything getting raised to then? What's the power? 2, and what's the root? No. 3. I'm doing this power and this root. I'm doing them both at the same time. So now every single one of these factors has to get raised to the 2/3. I have to do 8 to the 2/3 because this is to the first. I got to multiply that. What am I going to get here if I multiply this? Negative 3 times 2 divided by 3. What is it? And then I've got b, and then I've got 6 over 12. So what's that going to be? 1/2. Alright, so what is the cube root of 8? To the second. So I have 4. If I have a to the negative 2, it has to go to the denominator. And then what about b to the 1/2? What does that mean? Radical b. Let's see, do I have any restrictions? No. Do I need absolute value? No. That's our answer. So these problems can look really difficult, and then once we start working with them, they turn out to be much simpler. Alright, look at number 20. We have 4 over 3 plus the 4th root of 4. Guys, we need to rewrite the 4th root of 4 because we have to get rid of this radical. When we have 2 terms in the denominator, the way to get rid of the radical is to multiply by the conjugate. But can you think of another name for the 4th root of 4? What's the 4th root of 4 also going to be? Just what? Square root of 2, because it's 2 to the 1/2. So another name for this is just radical 2. Now we multiply by the conjugate. The 3 stays the same. We change plus to subtraction. We're going to do that in the numerator and denominator. In the numerator, 4 times 3 is 12. 4 times radical 2 is 4 radical 2. In the denominator, I get 9. What happens to the outers and inners when we have conjugates? Cancel out. What's radical 2 times radical 2? Just what, guys? 2. So now we're going to have 12 minus 4 radical 2 over 7. This is totally fine, but if you're looking at multiple choice, it could be written like this also. Just be aware that those are the same thing. All right, look at 24. What have I been saying? What do we always want to get? To be able to work with these, we have to have like bases, right? Like bases. How can I rewrite this then with a base of 2? 2 to the what? 2 to the second, and then what root are we taking? 5th root, so it's 2 to the 2/5. How do I rewrite this? The cube root of 2, how's it rewritten? 2 to the what? 1/3. Divided by, that's going to go in the denominator. How am I going to write it? 2 to the what? 2/15, good. So what do I do if I'm multiplying and the bases are alike? What do we do with the exponents? Add them. What do I have to do if I want to add those? Get a common denominator. This would be 15, this would be 15. This is going to be 5 times 3, 2 times 3. 3 times 5, 1 times 5. So in the numerator, I really have 2 to the 11/15. In the denominator, I have 2 to the 2/15. What do we do when the bases are alike? What do we do with the exponents? Subtract. What are we going to get? We're going to get 2 to the 9/5, but what's 9/5 going to, or 9/15 going to be? 3/5. Can you rewrite that? How's that going to look then in radical form? We're trying to get radical form. What's the root? So it's the 5th root of what?
8.
Good. So all of this is just the same thing as 5th root of 8. All right, this one looks fun. I like it. The more stuff going on, the better. All right, we're going to work from the inside out. What's another name? We've got an 81 and a 27. What's a common base I can get for those 81 and 27? 3. Okay, let's work from the inside out. It's not going to be bad, I promise. We have 3 to the 4th. But what root are we taking right there? 3rd, right? Okay, so I took care of this, I took care of this. Now, is this a root or a power? Power, and what's this? Root. So now I have this to the 3/4. Okay? In the denominator, let's look at what we've got. What's 27? 3 to the 3rd. What's the root I'm taking? Square root. And then we're also taking what other root? 3rd root. See, by using these rational exponents, we can simplify this. Using just radicals, it's too hard to do. But if you use rational exponents, it goes pretty well. What's 4/3 times 3/4? 1, so this is 3 to the 1st. What's this going to be? 3 to the 1/2. All right, so think about it. What is this, the simplest radical form? What is it? It is You get a Smartie for being smart. I don't think I can throw it over there. You think I can? Oh my gosh. Oh no, watch out. I'm sorry. Alright, he is correct. These bases are alike. We subtract the exponents. And then it is radical 3. He was correct on that. Bases alike, subtract, rewrite.
I was like hoping that way you would throw it short, that way you could catch it.
Yeah. You didn't get this? What did you get, Riley? I was talking to Riley.
Oh, I got it, but like, I don't get how you set it up.
How I did it way back here?
Yeah.
Okay. So, 81's 3 to the 4th, but I was taking the cube root. Then I was raising to the 3rd power, but I was taking the 4th root.
Okay.
So that's this part. For this part, I'm dividing, so I put a bar to divide. And then this is 3 to the 3rd, but we're taking the square root, and then we were also taking the cube root, so that's 1/3.
I don't get why it's like, so I get you're taking, I get when you get like 3/4, but I don't understand like why it's 1/3 instead of 2/3.
Oh, that is because, see, it's the cube root of 3 to the 3/2. Do you agree with that? That this is 3 to the 3/2? So then the cube root is just 1/3. It wouldn't be 2/3 because that would mean I'm squaring it, and I'm not trying to square it.
Oh, okay. I see what you're saying.
Okay. So radical 3.
Thank you.
You're welcome. Okay, 32. Bases alike. What do we do with the exponents?
Add.
Keep the base, add the exponents. What are we going to get if we add those?
2A.
2a. Okay. 2a is 1a plus 1a, 2a. What's wrong? Were people saying other stuff?
I said 0.
Oh, a plus a is 2a. All right, we got that settled. Okay, so this could be 7 to the 2a, but it could also be 49 to the a. Would you recognize that those are the same thing? 7 to the 2a is 49 to the 1a? Okay. All right, now for the one that is the most fun. I like this problem. All right, one step at a time. We've got a 27, we've got a 3, we got a 3, we got a 9. What base should I use? 3. What is this going to be? 3 to the what? 3rd, and then what root? 2. What do I do if I have a power to a power? Multiply, okay, so I'm going to have 3, and then I do 1 times 2 is 2, plus radical 5 times 2 is 2 radical 5. What do we do if we're dividing by a fraction? What do I do to the second one? Multiply by the reciprocal, right? So this is going to go to the bottom. How do I write radical 3? 3 to the what? 1/2. 9 is going to be 3 squared, and then it's still to the radical 5 minus 1. Got to use parentheses around that. Alright, now, when I'm multiplying, does multiplication follow the commutative property? Can I multiply in any order? Yeah. If I'm doing 2 times 3 times 4, can't I do 3 times 4 times 2? Same thing. So here's what I'm going to do. See how these kind of match up and these kind of match up? Since I can multiply in any order, I'm going to switch these two around. So I'm going to write 3 to the 3/2 over 3 to the 1/2 times 3 to the 2 radical 5 minus 2 over 3 to the 2 plus 2 radical 5. We need to zoom in on this one. Alright, see what I did? Multiplication is commutative. I just decided to switch these two. Totally allowed to do that. What do we do? Bases alike. What do I do with the exponents? Subtract them. What's 3/2 minus 1/2? 1, so it's 3 to the first. These have like bases. I have to subtract. What's 2 radical 5 minus 2 radical 5? KK? This is what you wanted to say before. 0, right. What's negative 2 minus 2? Not 0. Negative 4. Alright, and now our bases are alike. We're multiplying. What do we do with the exponents? Add them. We get 3 to the negative 3. Anybody tell me what that would be at the end? 1 over... Well, you got it. 1 over 27. So that whole mess right there is just 1 over 27. That's something you would see on Math Facts, though. You know that test we took where you got bonus? Something like that. All right. Yep.